Okay, hello everyone. Thank you all for joining us today for the second research talk of the AI and data science theme. So it's a great pleasure today to have Dr. Neil Urquhart as our speaker today. Neil is an associate professor of computer science at Edinburgh Napier University. His research interests include real-world applications of AI, particularly in the transport sector. Recently, he published a book on nature-inspired optimization for delivery problems. And today he's going to talk about whether evolution can help develop public transport networks. So over to you, Neil.
Thank you, Dimitra. First of all, can I just confirm, can everybody see my slides? Are they sharing correctly?
Yep.
Excellent. So this work is very much a work in progress. I don't know how this is going to end, as it were. I don't know how successful or unsuccessful this will be in the long term. I have, over the past 5 or 6 years, worked with a number of organisations on public transport related projects. One of the things that had been at the back of my mind during that time was whether or not we could use optimization and AI techniques to look at the fundamental problem of actually designing public transport networks. And I'll talk a bit more about how we've got where we are with our public transport networks and some of the implications of that. The gem for starting this particular piece of research was actually doing some work with colleagues from Oxford Brookes and Bath University's mathematicians, where we were looking at city centres and looking at data, and that highlighted to me just the amount of data that is now available to us to allow us to better understand these landscapes. And so what followed from that was this project, which is very much trying to, at the moment, just trying to answer whether in principle we can develop public transport networks using optimization techniques. So the problem we have is that public transport networks exist to address a great many requirements. So just about everybody who journeys on public transport has a different problem that they wish addressing. They wish to go from some place to someplace else. Almost invariably, they actually want the public transport network to be slightly different to what it is. What we actually want is a bus that stops right outside our house every morning and takes us directly to our place of work and drops us off right outside. We don't get that. We get something of a compromise. We also have to accept that public transport networks not only have been formed to serve the needs of the passengers, they've also been formed around technical needs of vehicles and technologies, around the operators, around operators' ability to fund networks, around the economic viability of them. And in the case of local public transport, certainly in Scotland, there's always been a certain political element as well. Politicians, particularly councillors, sometimes get elected on the basis of putting a new bus stop in a particular place, or campaigning to have a particular bus service introduced or changed. So there's a certain political element there. The public transport network that we have in most UK cities has evolved over a long period. So small changes are introduced to the network, changes that are deemed successful by the authorities remain, changes that result in less success, whatever success may mean, are often overwritten by the next round of changes. There tends to be, certainly in bus networks, less so in rail networks for obvious reasons, but there tends to be in bus networks almost continual small change. This having these networks which have been long established with many small changes leads to trust of this established networks amongst its users. And one of the things that I'm interested in is how do we explore changes to the network that balance novelty with that familiarity that already exists. So just a case study in Edinburgh. Edinburgh, the current public transport network that people use in Edinburgh actually can trace its beginnings right back to the first horse trams in 1871. And since 1871, what has happened is that essentially services have been extended, things have been changed, but at no point in that has there been a blank sheet of paper approach taken to it. It has continuously evolved over that time. It's evolved through technology, horse trams to cable trams to electric trams to motor buses, and now back to trams, and in the future increasingly to electric vehicles. But you could argue that in many respects what has happened here is that the network has evolved. It's been an evolutionary rather than a revolutionary process to get where we are. And that means that the network that we have in most of the networks we have in our cities at the moment are widely trusted by users. So to give an example, my mother travelled to her school in the 1950s as a schoolchild on a number 16 bus. I travel to work on a number 16 bus. It runs pretty much down the same streets that my mother travelled on it a generation before me. That level of trust of the transport network fundamentally being a known entity is incredibly important. And that makes transport operators very reluctant to get involved in schemes which suggest radical sweeping changes. They like small adjustments to the network that they can quantify, and adjustments that don't leave passengers in facing an unfamiliar network. So the problem I started looking at was the problem of how do we route buses through the centre of Edinburgh? So a small problem at this stage to begin with, and I was inspired actually by this particular map, which appeared on Flickr. A copy of it appeared on Flickr, and essentially it describes the centre of Edinburgh just before the tramway was constructed. And for this initial study, I've opted for Edinburgh pre-tram, simply to make this particular model a bit more straightforward, easier to implement. As we'll see in future work, updating this to take account of other transport modes such as trams is very much on the agenda. The problem we're looking at, there are 18 services that operate across the city centre. Each of these services operates in two directions, and each of these services operates in two directions, and they all continue to the outskirts of the city. So this is only for people who are not familiar with Edinburgh. The majority of bus services in Edinburgh start on the edge of the city, travel into the city centre, through the city centre, and back out to the opposite edge of the city. Most of them travel, for example, north to south or east to west, going through the city centre. And at the moment, our interest is in looking at that central area. So it was some initial experiments looked at using techniques such as map elites, but in fact it was suggested that really novelty search was the way to go. And so what we have done is the novelty search has we have utilized novelty search to come up with ideas. And what we're trying to do here is come up with ideas for the transport planners. We're not trying to tell the transport planners this is what to do. What we're trying to do here ultimately is to suggest changes, and in particular, perhaps to suggest changes that they wouldn't have thought of. One of the issues with a very established public transport network is that perhaps sometimes the planners themselves get a bit too established. So, you know, you speak to public transport planners and they'll say, well, we've never run a bus up that street. Why? Oh, well, we just don't do that. Oh no, buses never turn left at that junction. Oh no, we've never done this before, so why would we do it now? And one of the advantages of novelty search is this random element, this idea that novelty search will just try things, and what it will do is it will look for examples of things that are different, that are in some way novel. So ultimately what we want to do is to use novelty search to find changes to the network, variants of this existing solution. And in the longer term, we want to be able to allow the user, the ultimate user being a public transport planner, allow them to be able to browse through these solutions, starting with the established solution that they're familiar with, and browsing through solutions that gradually move away so they can balance novelty, which they need in order to encompass new developments, new ideas, new changes to the city, with this familiarity, so that the majority of their passengers are not left in an unfamiliar situation. So in terms of the data that we use, this graphic here, this is the actual data set that we deal with. So fundamentally, we deal with OpenStreetMap. OpenStreetMap gives us the imagery for maps. It gives us bus stop positions for all the existing bus stops. It gives us the underlying street graph. Each of the white squares in that diagram represent a bus stop. Some of them, it's not flagged on the diagram, most of them are established bus stops, but a selection of them are bus stops that are not currently in existence, in order to allow us to explore where it may be desirable to add new bus stops. One of the issues with planting bus stops are that there's a great many restrictions as to where you can put them in terms of practicality. So what we do is we predefine all the areas where a bus stop might be placed, and the problem is not so much placement but selection. As well as OpenStreetMap, we use publicly available publicity materials that tell us about routes and so on. And an incredibly useful data set is the Scottish Assessors Association, who have a publicly available data set of commercial properties for tax purposes. And we'll come a bit more to their data in a minute or two, because it really lets us build up a picture of what is in the city centre and where. So Scottish Assessors Association, for the they classify properties under these headings. There's a couple more that we filtered out. One is advertising, which we filtered out because essentially it's advertising, hoardings, funeral homes, and I think there was one which is basically anything else, and one for, I think, for electricity substations. So after a little bit of sanity checking, that's what we are left with. So there are 33 properties which are deemed to be education and training, 23 properties which are deemed to be education and training in the centre of Edinburgh, 26 which are associated with health or medical use. Unsurprisingly, offices seems the majority of commercial property in the centre of Edinburgh, offices, followed by shops and hotels, which, if you know Edinburgh, these numbers are probably not surprising. And these are the numbers, so we label each of these as being a point of interest. One of the things we're interested in doing is saying, well, to what extent do our bus routes service these points of interest? So if a bus stop is within 250 metres of a point of interest from the Scottish Assessors data, it's deemed as serving that point of interest. Once we've established everything that's served by a particular route, we only count a point of interest once, even if it's within 250 metres of 2 stops on that route. That some of the stopping positions in the centre of Edinburgh, some of the bus stops are potentially so close together that it's possible that you could end up double counting the same point of interest. So a major part of all this was, how do we represent our solution? How do we represent a solution to this problem? So each individual solution comprises, for each of our routes, a path from the entrance point in the city centre to the exit point, the path that it takes through the city centre, and the stopping pattern for that route. So as each route makes its way through the city centre, it will pass bus stops. Some of the stopping pattern defines which of these bus stops will be serviced by that route. Now, in the city centre, it would not be desirable for every bus service to call it every bus stop that it passes. That would simply lead to too many stops being used. It would slow services down to too many stopping points, and it would lead to many of the stops simply becoming congested. So part of what we have to do is to work out that stopping pattern. One of the problems that beset this work at the earlier stages was coming up with bus routes. Traditionally, when I've been involved in vehicle routing type problems, you simply ask for a path from A to B. If you're doing a logistics problem and you're dropping off goods or parcels at various points, you simply ask for a route that takes you through various points, dropping off. Bus routes are slightly more restricted. First and foremost, no loops. You do not want a bus service that essentially goes round a complete loop in the centre of town, going down the same street twice. There are certain turns at junctions which are prohibited simply because buses are unsuitable to make that turn. There are certain streets where buses are prohibited. These prohibitions are not always advertised. In many cases, they're often at the whim of the bus operator. So the bus operator, whilst it may be legal for a bus to be driven down a particular street or make a particular turn, a bus operator might actually decide that they don't want any of their services on that particular street or making that particular turn because it's viewed as being potentially risky. We also want to avoid a situation where stops are shared by the same service going in different directions. So, for example, if we consider the number 16 bus, use the 16 because it runs close to Napier. The number 16 bus runs north to south over Edinburgh. We don't want the northbound 16s and the southbound 16s ever ending up calling at the same stop if we can avoid it. That becomes incredibly confusing. The way that I got round this was actually to realise that, in fact, what we do is that we come up with a set of predefined variants for each service. So rather than have the algorithm decide exactly where each route should run, what the algorithm does is it chooses between a set of predefined variants. So this example here, this is service number 23. So it enters the city centre at the bottom here at Toll Cross, and at the moment it follows the black line running down George Forth Bridge, down the Mound, and across George Street and down into Newtown. And at both ends of these, it continues for several miles further to the north and to the south. And what we do is, because we turn our service network into a graph of streets, there we can simply use pathfinding algorithm within the graph. So for network X in Java, there's a function called simple path, which will simply find all the paths up to a certain depth between 2 points. And so using that function, we can predefine a whole bunch of other candidate routes We can also sanity check these routes manually when they're generated to make sure that none of them do contain loops. So for the case of the 23, the alternative services occupy the various permutations around these streets in red. So you can see that, in fact, what's been identified as a possibility of running the 23 down Lothian Road and along Princes Street, and various permutations of running around over George Street. What we did was essentially we used the simple path function and told it to search up until it found at least 5 routes and stop at that point. So we found on average 5.8 possible variants for each route. And one of the advantages of this approach is that we could, if we wished, a transport planner could, if they wish, put in their own particular variants. If there were some particular route variants that they wanted to try, that they wanted to evaluate, there would be nothing to stop them being added manually. So you'll see in each case, we define a route as the service number. That's the number that would appear on the front of the bus that will be familiar to you if you're in Edinburgh. The letter at the end basically gives a direction. So service number 1, we have 1 east, which is it in one direction, and 1 west, which is it going back in the other direction. So we can, because we have small numbers of variants, we can effectively pre-check them for sanity. And as I say, it would be possible in a commercial context with developing this further for a transport planner actually to have some of these services with only the 1 variant, so they would never be changed, and some with specific and some with specific variants. So stopping patterns, as we've already talked about, as well as each of these variants is actually a list of bus stops that define the route to be followed, and essentially each bus stop has a bus stop flag, a 1 or a 0. 1, the service will call that stop, a 0 it does not. So our mutation and our mutation operators, as we'll see, involve changing that stop pattern to take a bus stop in or out of a route, or changing the variant to actually change the route being followed. So we have our solution. It is solutions essentially are this list of services and this list of bus stops for each service, with 1s or 0s defining as to whether or not that stop is in use. So to mutate, to randomly change that, to try something new, we can either change the variant, change the path variant to a different option for that route, or we can change the pattern of the stops. For crossover, where we want to take 2 solutions and create a new one from it, we simply create a new solution base by taking services from each of the parents. So each service is the new solution has each of the services, each of the 38 services that go across the city centre are there, but the variant of that service will come randomly from either one of the parents. In terms of evaluation, so at the moment, in terms of evaluation, we have 15 criterion that we evaluate for. So 15 things that we evaluate any solution for. The first setup here, care facilities, cultural, etc. These are the number of points of interest served. The distance is the total distance travelled across the city by adding up the lengths of all the routes. Interchange is the ability to measure transfer between routes. So every time 2 routes share the same stop, it scores 1 on interchange, and essentially the higher that interchange score, the easier it is for passengers to get from one route to another. In a city like Edinburgh, where all the bus routes come from the outskirts and go into the city centre, interchange is incredibly important, because your ability to get from one part of the city to the other is often based on taking a bus into the city centre, changing to another route and getting it out the city centre to your destination. Stops over. So at the moment, there is roughly an average, I think it's of the desirable number of services to have at a particular stop is roughly 5. So we look at the number of stops that have more than the desired number of services calling at them. Average stop use is the average number of services calling at each stop. Stops used is the total number of stops that are in use in that solution. New stops are how many of the stops that are in use by the solution are there stops that were defined by us that are not already there. So essentially, in economic terms, stops used, there is a cost. Each bus stop has a yearly cost in terms of maintaining it. New stops have a capital cost as well in terms of establishing them. And finally, familiarity, which I'll come to in a minute or two, familiarity is how familiar is this solution to passengers who are using the current solution. So we have an established solution. These are the stats of the established solution. The established solution is based on the routes as they were basically as they were just prior to tram construction. You can see there the total, it was 169 kilometres of running around the city centre, and we can see predictably we served lots of public houses, lots of offices, it being the centre of Edinburgh, lots of cultural attractions, nothing in terms of health or medical, which is interesting. But then if you know Edinburgh and you think about it, there are no hospitals or other major medical facilities within that central district. I think care facilities includes dentists, GPs, and so on. What we're more interested here, though, is we note that the familiarity of the established solution is 1. And I'll come to that in a minute or two, but essentially a score of 1 means that passengers will find that is exactly as it is at the moment. As that goes down towards 0, it becomes less familiar, and I'll tell you how we calculate that in a second or two. 25 of the stops in use have more than 5 services calling at them. There's an average of 5.5 services call at each stop, and there are 108 stops in use in total, and no new stops. So that is as we'd expect, because the established solution doesn't use any of the additional stops that we've defined as possibly being available for the future. So this business of familiarity, this took a bit of time, and there's been quite a lot of research in terms of optimization in comparing solution, calculating different distances between different solutions. And one of the things I was interested in was, how do you come up with the distance between a new solution, a new idea, a new bus network, and what's there at the moment? And the answer, having spoken to some contacts in the public transport industry, the answer actually was very straightforward. They suggested that the answer was actually simply come up with a list of services and stops. So for every bus stop, come up with the pairing of all the services that call at that stop. Then for a novel solution, how many of the bus stop pairs in the new solution are in the existing solution? If they're all there, then every bus stop has exactly the same service as it does at the moment. So any passenger turning up to use the bus will notice no difference. Conversely, if that dropped to 0, no bus will call at any stop that it calls at the moment. Passengers would find it chaotic and unrecognisable. One of the things this doesn't do at the moment, and there was a bit of debate over this, but if we add additional stopping points to a route, it doesn't alter the familiarity. The familiarity was based very much on the concept of a member of the public using the bus network. How will they perceive the changes? So a familiarity of 1 means they will notice nothing different. There may be additional stops, there may be more services calling at the stop they're at. The service they use may call in more places, but all the current stops are still in use. So there will be nothing that they do at the moment that they can't do after the change. So our basic methodology, so we run novelty search. One of the reasons why we like novelty search is it makes random changes and it favours keeping solutions in an archive if they represent something that is sufficiently different from what is there. It has no built-in bias, and speaking to quite a few people, friends and contacts in the public transport industry, there is an awful lot of, well, we've always done it this way, so we'll keep doing it that way. Sometimes a reluctance to try something new because it simply hasn't been done before. Novelty search has no bias built into that. It will try out combinations of things, and it will favour them if they are viewed as being sufficiently different from what is there. So we run this novelty search 10 times because there are random elements to it. Always repeat 10 times. Having made 10 runs, novelty search, when it has run, produces an archive of solutions, say a big long list of possible solutions. So in our case, what it produces are a whole bunch of variants of the public transport network, which might be of interest to us. What we do is we take these 10 archives and we combine them, removing any duplicates, into one larger archive, which forms our ultimate solution. So for those who are interested, this is novelty search algorithm that we use. We start out with an empty archive. We have a population of 25 solutions, which represent 25 slight variants, initially very slight variants of the network. And then over time, we make gradual changes to these. We mutate them, making a random change to them. We recombine them by taking two different solutions and making a new one by bringing elements of the two together. Over time, we add things to the archive as if they are seen, if a new solution is being seen as sufficiently different to what is already there. So in terms of experiments with where we are at the moment, I wanted to answer through the experiments 3 questions. First question is, what is the relationship between things that novelty search finds and our existing established solution? Then I got into what is the effect of seeding this initial population with the established solution? And finally, for the moment, how can we balance novelty with familiarity? How can we balance change with familiarity? So, first set of results. Initially, we ran novelty search, and we simply let novelty search go from a standing solution, and we asked it to find variants of the existing network. There is no particular target for novelty search. Its job is simply to find lots of different solutions that we can then browse through. And here are the 15 characteristics that we look at our solutions by. And each of these is graphed against familiarity. Now, what is interesting is that this orange dot represents the established solution. The blue dots represent the things that we found. In every case, it didn't find any solution that was anywhere near what's already there. So, left to its own devices, just allowing the evolution to run, it doesn't find anything like what we already have. What we did find when we run it is we get approximately we find approximately 14,200 solutions every time to browse through. We consistently find roughly the same number. So however, one of the things we want to do is we want to find a set of new solutions where we find some that are very similar to what we have. So when we allow a transport planner to browse the solutions, looking at new things, they can start out with the current solution that they're familiar with, that they trust, and initially look at solutions that are very similar. And then gradually, as they browse through the solutions, move further away. But the problem is, where we have things like, see the first column here, which essentially is the graphs we just looked at, we can't. If you start browsing on that first solution, it is a big jump to anything new. So next thing we did was we took our established solution and we used it as one of the 25 initial solutions that is used to seed novelty search. That gave rise, we call this the single seed, that gave rise to this column here. And what we discover straight away is the effect of even just providing access to that one solution changes things dramatically. Now what we find is that we start evolving solutions with a much higher familiarity. That solution, that little injection of genetic material at the start, through the recombination and the crossover, spreads to the population, and we now find that if we were to start browsing through these solutions, there will be a few solutions that are similar. So that's heading in the right direction. Keeping going on that theme, we then decided, well, what happens if you take the entire initial population, have one based on just a copy of the established solution, but the other 24 being variants of the established solution. So essentially the whole process has its roots and starts from that established solution. We get what I've termed fully seeded, and it extends the principle slightly more. We find slightly more solutions, but what we find in every case is that if we were to start browsing from this established solution, there are other solutions now that are closer. Now that brings us some way towards what I want to do, which is the ability to build a tool that starts with this established solution and then allows the planner to browse through solutions that initially are very similar. A little bit of stats. We did a quick t-test on the problem sizes, and we first of all we looked at for each of these, for the no seed, the original, with the single established solution, and with everything from the established solution, we also looked at those that have a familiarity of over 90%. So initially, nothing. Then if we seed with the established, we start to see that there are some solutions appearing over 90%. For the entire population derived as we'd expect, we're finding far more of these familiar solutions. These are the solutions that will be very similar to what is there, that hopefully represent small changes to our current solution. And if we if we just do some stats and we do a t-test looking at the solutions over 90%, we discover that, yeah, these are, as we'd expect, these are statistically significant, going from 0 to 0.3 and then ultimately up to 1.4. These are significant changes. They're not enough though. At the moment, my view is this is only just the tip of where we want to be. The final experiment at this stage was looking at how do we balance novelty with familiarity. So this, I think, is crucial to it all. And at the moment, what novelty search does when it starts, it measures the novelty of a solution as its Euclidean distance in terms of all of the 16 characteristics from another solution. So it takes that and basically calculates in 16 dimensions the difference between them. The further apart the solutions are, the more novel they're deemed to be. And to be included in the archive, what we do is we look at that distance. We look at the distance for a new solution between the new solution and the 10 closest, most similar solutions by this measure in the archive and the population. If we take that distance, we average it. If that comes out as greater than 1, then we say, okay, this is sufficiently different to what I've seen before. I'll put it in the archive. However, that doesn't really bias it in favor of familiarity. So given that familiarity exists in a range of 0 to 1, what we did was we simply altered the novelty so it took the distance and multiplied it by familiarity. Now, what that meant basically was that things that are closer, things that are more familiar, have a higher novelty value. The hope being that what this should do is that things that are close to in the range of being closer to the familiar solution, but are closer to the familiar solution, but are novel, that are certain distance away from other solutions, will hopefully be favoured. So what this should do is continue to favour solutions that are more familiar, and we see that it does to a small extent. It does. If we do some t-tests for significance, again looking at the percentages, what we discover is that if we look at the solutions with over 90% familiarity, so that's kind of where I'm interested in at the moment. When we go in here and we change novelty to distance times familiarity, and we'll say seeded with the whole population derived from the established, as that seems to be where we are, we are slowly starting to move the percentage of familiar solutions up, but it's still small. It's still less than 2% of the archive. There is still some way to go. So at the moment, my thinking is looking at how do we push the evolutionary and the search process into really favouring these solutions that are close to where we are at the moment, and coming up with more solutions with this high familiarity rating, again, to give the maximum number of initial solutions for a planner to look at when they are trying to move from the established solution into something new. So some very brief thoughts on visualization. This is one particular visualization that I've been playing with over the last few weeks. Visualization is not really my area. My area is more optimization. So this is an area where if people have ideas and suggestions, I've been very happy to hear them. This particular idea looked at an idea of our established solution being in the middle, each of these lines effectively representing one of our criterion, and each of these representing, each dot representing another solution, these being the solutions that are adjacent in each criterion, i.e. higher or just i.e. adjacent in terms of higher or lower to the root solution. What we discover very quickly is that most of them, as we'd expect, given that only about 2% exist in this familiar zone up here, familiarity being the closer we are to the centre, the more familiar it is, we find that most of them are really too far away to be desirable. Just though, to have a look at an example, apologies, I have a dodgy mouse which is going backwards and forwards. If we just zoom in on that, for example, suppose we were interested in saying, well, how can we increase the interchange of our network? What could we do to make our to make it easier for members of the public to change bus? We could look at that and say, well, hang on a second, interchange greater. Yep, there is a solution that takes interchange, increases it by 1. It's that solution there. Full disclosure, the labels on that diagram are stupidly offset. That's because I used ChatGPT to help me write the code to draw the diagram. Lesson learned. Well, increased interchange. So if I find that solution there in the archive, 112042, which is just its arbitrary index in the archive, if I dig that solution out, first of all, I can visualize it and see. So this is this column here is the established solution. This is this slightly changed solution. It is very similar. We don't actually see that many. If we look in the changes column, there's not that many changes to it. I can then say, well, can you show me what bus services are different? And in this case, it's route 36 is different. And this plot here shows me the 36 route from the start to the end. The yellow being the route that it's taken at the end of all this. Each of these labels represents a bus stop. The ones with the little sort of gear, these are stops that were there before and are still there. They haven't changed. The ones with a red X, these are bus stops that were in the established solution that we've moved away from, and the ones with the green plus are stops that are new to that route. And to sanity check it, what is it actually saying? Well, it's saying take this route and take it up Market Street, down the Mound, and add an extra stop in Princes Street. What it's basically doing is it's adding more stops to that route on busier streets. So it is in fact, so it's doing what we asked to, it's increasing interchange. And it's rather nice at this stage in this work, where we're still trying to do this sort of very early proof of concept, to be able to follow through an idea like this, put it on a map and say, well, actually, yeah, that makes sense. There is the glimmer here of some common sense, of something that actually makes sense in the real world. So, conclusions. What is these initial experiments, this initial study, what is it? What have we learned from it? Well, we can support public transport network design and development. We can use methods such as novelty search. They will find lots of solutions. They will find solutions, some solutions which are similar, but there's a lot of room for improvement. Pure novelty search doesn't find solutions that are similar to the established solution. We absolutely have to use the established solution as part of the search. We have to use that as our starting point, and to some extent, that makes a great deal of sense. Starting from a random starting point, there is no guarantee that we will find solutions that go around this arbitrary point in the search space that our existing network is. So that makes a lot of sense. Seeding with the entire initial population from the established solution, I wasn't sure whether that would work, whether that might actually make it too biased, but actually it works quite well. We still find solutions that are a long way away, but we find far more that are closer. And balancing novelty with familiarity also at present seems to work. It's also giving us more solutions that are in this highly familiar area. So, taking this beyond the proof of concept. So, I am at some point going to be taking this to various colleagues who are in the public transport industry, more formally. Sure, most of them know about this and have given some advice, but at some point I will be taking this to them and giving them a more formal demonstration. What, however, do we need to do before we can show this to public transport planners and get taken seriously? Well, we need far more solutions that are familiar. We need lots and lots of solutions that are right up there, that are just very simple variants of what we have. We need this ability to start off with our current solution, our established solution, and then go through these small mutations, small changes, and allow the user to troll through them to find what it is they're looking for. We also need to look, keeping directional routes closer together. So generally speaking, at the moment, it will tend to develop if, for example, we have, again, the number 16 bus, we have 16 northbound, 16 southbound. At the moment, it will tend to develop these two routes separately. So we need to look at altering the representation and the structures so as to keep routes, to encourage them to stay together. They can't, of course, the problem is that city centres with all their turn restrictions, one-way streets and so on, don't always inherently encourage that. And finally, we still need a better methodology for visualising and browsing solutions. That's something I'm looking at. At the moment, I'm also looking at using parallel coordinates. For those who know that, I've been looking at doing some parallel coordinates. Part of the problem we have, though, is that the sheer number of solutions we're generating are making visualization rather difficult. So these are the things we need to address before I think we can take this to people in public transport and get it taken seriously. So generally, what does that mean? Future work, better means of exploring solutions. One possible area for that actually is thinking less about visualization and perhaps more about using machine learning to process the archives and actually and then use what is learnt from the archives, i.e. the relationship between changing routes and changing bus stops and changing characteristics, and actually whether machine learning can be used to effectively look through the archives for us. We need to increase this for other transport modes. So in particular, we want to add the tramway and then bring the established solution up to date. That has the interesting effect that it would actually allow us perhaps to see much more the effect of adding the tram into Edinburgh. We also need to think about route frequencies and vehicle capacities, because public transport is not just about paths and routes. And then it would be very useful to have a what if analysis. So the classic thing, you speak to public transport planners, they spend an awful lot of time working out what to do if a particular street is closed. That can be because, if we look at the news, for example, centre of Glasgow, a bunch of streets around Central Station have been shut for a while. Very suddenly, very unexpectedly, there was a need to come up with a revised network on a temporary basis. But there is also, in the centre of Edinburgh, for example, there are frequent schemes and proposals to pedestrianise this area or pedestrianise that area. So how can we adapt this to actually look at saying, well, can we do what if analysis? So can we actually set this up to say, okay, I want you to explore solutions, but I want to explore solutions around no bus services on this street or that street. And again, in the world of novelty search, where we can come up with many solutions and we can browse through them, we can perhaps differentiate between coming up with a solution that is effectively an emergency temporary diversion around a closure and coming up with a solution which represents more radical change, perhaps a less familiar solution around a street being pedestrianised permanently. And one of the fundamentals is scaling this up. At the moment, we're only looking at the city centre. That's only a small part of the picture. Very interested in the longer term in extending outwards and looking at entire bus routes. There is a very useful data set that we've used in other work, which is the postcode data set for the UK. Interestingly, tells you how many households are in each postcode, which gives you an indication of how many people live there. But also gives you an index into the Scottish Index of Multiple Deprivations, which tells you something about the socio-economic status of these households. That data get taken together has the potential to tell you around a particular, in the catchment area for a particular bus stop, how many households are there and what sort of households are they? Are they likely to be good bus passengers? You then begin to get to the stage where, if you scale this up, you can actually start to look at saying, well, taking the points of interest from Scottish Assessors data, how well do we serve particular households? How well do we allow households in that postcode to get a bus to hospital? How well do we allow people who live in that postcode, how well do we allow them to get to shops and offices? So we can do a lot more as we scale up, particularly because there's a lot more out there in the way of data. That brings us 2 minutes to 5. So thank you very much for listening. Any questions?